What is up, my dear students? Hope you all are doing good. For the students who have given JEE mains this September, if you have done well, then congratulations. If you have not done well, then no problem, no need to fret. It is totally fine. So today let us take a look at a question from JEE Advanced 2016. This question is from the EMI chapter. Let us first analyze the question. So, a rigid wire loop of square shape has side of length L and resistance capital R. So, you can see here this is a rigid wire loop of square shape and it has a side length L and resistance capital R. I have drawn it little thick so that it is easy for you to visualize it. This wire loop is moving along the x-axis with a constant velocity v0 in the plane of the paper. So this wire loop here is moving with a constant velocity v0. At t equals to 0, the right edge of the loop enters a region of length 3L where there is a uniform magnetic field B0 into the plane of the paper. So you can see here that there is this region where there is magnetic field B which is pointing into the plane of the paper, and this is x equal to 0, L, 2L and 3L. So from 0 to 3L, right? So from 0, length 3L he is saying, right? So from 0 to 3L we have this magnetic field which is inside the plane of the paper. For sufficiently large V0, the loop eventually crosses the region. So he's saying this V0 is sufficiently large such that this loop crosses this region. Let x be the location of right edge of the loop. So the location of the loop is given by the where this right edge is. So let us say this right edge is here, which means the loop position is x equal to 0. If this right edge is here, then the loop position is x equal to L. Let Vx, Ix and Fx represent the velocity of the loop. Okay, so Vx represents the velocity of the loop, Ix represents the current in the loop and Fx represent the force on the loop respectively as a function of x. Counterclockwise current is taken as positive. Okay, so if current is moving in this direction, he's telling us to take it as positive. If the current moves in this direction, then we have to take it as negative. We need to plot v of x, I of x and f of x as a function of x. So we need to plot the velocity, the current in the loop and force on the loop as a function of x. So firstly, you're seeing these pink color spheres here. These pink color spheres represent the charge, positive charge, and the movement of these pink spheres will represent the direction of current in this square loop. See, in a conductor, it is the electrons which move and there is current, but to visualize current, so that there is no confusion in visualizing current, I have taken these as positive charges which are moving, and the movement of these gives you a sense of direction of current. This was a multi-correct option question. In each of the options he had given velocity as a function of x, current as a function of x and force as a function of x. Basically he had given us graphs. What we will do is we'll plot v of x, I of x and f of x as a function of x, and later at the end we will see which options are right. Let us now visualize what is happening in the question. So what we can say here is, as this wire loop goes into the magnetic field, there is a current which is induced in this loop, right? And after it enters the magnetic field, the flux due to magnetic field in this loop is constant, and again there is no current. And again when it goes outside the magnetic field, there is current in the loop. The direction of current in this loop can be found from Lenz's law. Now for each of these intervals, when the wire loop is from x equal to 0 to L, L to 2L, 2L to 3L and 3L to 4L, we'll analyze how the velocity, current and force on the loop changes. First, let us analyze the current in the loop. So let us recall that the location of the loop is nothing but the location of this right edge of the loop. So if this right edge is at x equal to 0, we say the location of the loop is x equal to 0. First, let us have a look at the schematic and just observe how is the current in this loop when it is going through the different regions of magnetic field. So initially when the loop location is from here to 0, there is no change in magnetic flux through the loop. So there is no induced current in the loop. Now when this loop starts entering the magnetic field, there is a increase in magnetic flux through this loop. So we can say from Lenz's law that there is a current in this loop in the anti-clockwise sense. So when this loop goes from x equal to 0 to x equal to L, there is a current in this loop in the anti-clockwise sense. So let's have a look. You see the current is in the anti-clockwise sense. Next, as it fully enters the region of magnetic field, the net change in flux is 0. So the current induced is 0. Now as this loop moves from x equal to 3L to x equal to 4L, the magnetic flux through this loop is decreasing, and again from Lenz's law we can say that the current in this loop will be in clockwise sense. So you can see that the current in this loop is in clockwise sense. And now after this loop leaves the magnetic field region, the net change in flux is 0 and the current induced also in the loop is 0. Next, let us analyze the force and velocity of the loop as it goes through the magnetic field. From x equals to this position to x equals to 0, there is neither current nor any magnetic field, so there won't be any force acting on this loop. When this loop enters the magnetic field, we know that there will be a current in the anti-clockwise sense. From the formula I into L bar cross B bar, we can say that there won't be any force on this part of the loop, on this part and on this part. Only force will be acting on this part. We can find the direction and magnitude using the formula I into L bar cross B bar. So this is the force. In this region there is no current, so there won't be any force acting on the loop. When the loop is moving from x equal to 3L to 4L, we know that there won't be any force on this part and this part of the loop. The only force on the loop will be on this part and from I into L bar cross B bar we can get the magnitude and also the direction of force. So the force is in towards left, and finally there is no current, neither magnetic field, and the net force on this loop is 0. Let us next analyze the velocity of the loop. We have been told in our question that a sufficiently large velocity is given to the loop so that it crosses the magnetic field. So this arrow here represents the velocity of the loop. The variation in velocity of the loop can be predicted from the force acting on the loop. So as there is no force, the velocity is constant. As there is a force in this direction, you can see the velocity is decreasing here. And right now there is no force on the loop and the velocity of the loop is constant. And once it crosses 3L, there is a force towards left, and again the velocity decreases, and after it exits the magnetic field, the velocity again becomes constant. One more question I have for you here is the velocity of the loop is decreasing, that is what you would have observed. So where is this energy going? Okay, so what we can say is that this kinetic energy of the loop which is being decreased, so that energy is going into the electrical energy of the loop. So if you put a bulb here, this bulb would have lighted up when the velocity of this loop was decreasing. So the total change in the kinetic energy of this loop equals the electrical energy which is generated in the loop. Let us move on to writing the mathematical equation for velocity of the loop as a function of x. First, let us analyze from x equal to 0 to L. So this here is x, this length is L, and say at this time the speed of the loop is v. So the flux through this loop is phi, which is equal to b into x into L. So I'm writing that here, x into L. The EMF it is induced in the loop equals to d phi by dt, which is equal to b into L into dx by dt, which is nothing but v. The current which is induced in the loop equals to the induced EMF divided by the resistance of the loop. So this is nothing but induced EMF is BLV divided by R. The force acting on this loop is nothing but I into L into B, specifically on this part of the loop. So the current value we get from here, which is BLV by R. So F equal to BLV by R into L into B. The net force on the loop is B square L square V by R equals to the mass into acceleration of the loop. We want the velocity of the loop as a function of x. So we will write a as a function of v and x so that we can get this equation in terms of velocity and x. Now we write this m into a as m into v dv by dx. We have got this equation in terms of v and x now. One very important point I want you to note here is, you see this b square L square by R is a constant, it is positive. The velocity v of the loop, it is in this direction. So the velocity v is positive. We can say that the LHS is positive. Let us have a look at the RHS. The mass is positive, velocity is positive. dx. dx means x final minus x initial in a very short period of time. That is also positive as the loop is moving in this direction. dv, which is v final minus v initial, is a negative quantity. So this dv in itself is a negative quantity. We have LHS a positive quantity and RHS a negative quantity. So we will put one minus sign here. So now the RHS will be of a positive quantity and LHS also will be of a positive quantity. Next, we can cancel out this v and v on LHS and RHS. We get dv by dx equals to minus times b square L square by R into m. Now dv by dx equals to some constant. We can say that the slope of the vx curve is a constant. If we integrate it further, I'm taking dx this side. So dv equals to minus b square l square by rm into dx. The integration limits, initially the velocity of the loop was v0 when it was at x equal to 0. At some x between 0 and L, its speed is v, which we need to find out. After integrating, we get v minus v0 equals to minus alpha x. I'm writing this term b square L square by Rm as a constant alpha. So finally we get the velocity is a linear function of x. Let us now plot the graph of velocity as a function of x. So from 0 to r, we have the velocity as v0 minus alpha x. From r to 3r, we have seen that the velocity is constant as no force was acting. Now from 3r to 4r, we know that the equations are similar as from 0 to r, and the velocity profile will be the same. So now if we plot the graph, we will get something like this. Okay, so v0 minus alpha x, the velocity is decreasing, then it becomes constant, and then again it decreases. After 4r, again it becomes a constant. Next, let us look at the mathematical equation and graph for I as a function of x. As we have discussed that current equals to b into L into v by r, we can say that the profile for the current will be similar to that of the velocity. So let us discuss that. So from 0 to r, we will have I0 minus beta x, where beta is some constant. From r to 3r, we discussed that the magnetic flux through the loop is constant. So the induced current in the loop must be 0. Next, from 3r to 4r, again there will be an induced current. It will have similar profile as that of the velocity. So we are writing that as I0 dash minus beta into x. We know that from 0 to r, it is an anti-clockwise current. So this has to be taken positive. From 3r to 4r, we know that it will be a clockwise current, and the clockwise current has to be taken negative. So I am just putting a negative sign here. So if you take a look at the graph, so current is decreasing with x, then it becomes 0, and then again also it decreases with x, but it is a negative value. Next, let us have a look at the mathematical equation and a graph for f of x. We have discussed that f equal to b square L square v by r, and from this equation we can see that the force also will have a similar profile as that of the velocity of the loop. So from 0 to r, f naught minus gamma x. From r to 3r, the force on the loop is 0. And from 3r to 4r, it will be f naught dash minus gamma x. Now as the force points towards left, which we have seen, I am putting a negative sign here and here. So let us have a look at the graph. So from 0 to r, we can see it's a linear function. It is decreasing and has a negative value. Then its value is 0, and then after that it again decreases linearly. So in the JEE exam, these were the options which were given. Velocity as a function of x, current as a function of x, another current as a function of x, and force as a function of x. And these are the three graphs which we have got. You can just compare here and see that the correct options are velocity as a function of x, and next current as a function of x. If you have not noticed and taken anti-clockwise current and clockwise current both as positive, then you would have put this option and you would have got a wrong answer. And the D option we can say is definitely wrong. So the correct answers are A and B.